Can we prove product rule in calculus? Product rule in calculus. The backbone of the calculus is integration. Calculus begins from integration. But when we are trying to find integration of an algebraic equation, then if we know the area, then it is all right. If we know the integration, then it is all right. Like polynomial equation, x to the power n, we know. Trigonometric formula, sin x, con x, cos x. If I know sin x, then I know cos x. If I know sin x and cos x, then I know tan x. Like exponential, logarithmic, everything we know. But still, if something that comes as a complex one, like sine square x cos x, what is the integration of sine square x cos x? We don't know. What is the integration of sine to the power 3x? We can think. What is sine square x cos x? What is sine x sine square x? That is sine x into sine x. What is the integration of sine square x? What is differentiation of sin x into sin x? Anyone would say, just go with the kind of product rule. So product rule is if you have a function fx and gx, fx into gx, what is differentiation of it? Fx, then differentiation of dx, gx. What is differentiation of fx into gx? That is the question. What is differentiation of fx into gx? Then fx differentiation of gx plus gx differentiation of fx. This is called product rule. But I was never satisfied. How to prove that it would happen this way? Differentiation of fx into gx equal to fx differentiation of gx plus gx differentiation of fx. This is product rule. If we talk about integration, again there is a product rule called integration by part. If I have a function fx into gx, what is integration of fx into gx? That is fx integration of gx minus big integration of fx, then differentiation of gx, whole big integration. Integration by part. Can someone prove it? Okay, very straightforward question. Can someone prove the integration by part or differentiation, product differentiation for the product rule? Differentiation of fx into gx is fx differentiation of gx plus gx differentiation of fx, or fx dgx by dx plus gx dfx by dx. This is called differentiation product rule in calculus differentiation, or integration by part, that is integration of fx into gx is fx and integration of gx minus big integration, and then inside it integration of fx and differentiation of gx. So can someone prove either of them? So we will start by integrate product rule in differentiation. So if we have product rule in differentiation fx gx, if there is a product rule fx into gx, then its differentiation is fx and differentiation of gx plus gx differentiation of fx. Okay, so that is the scenario. Now can we prove this differentiation product rule in differentiation? Can we prove this product rule in differentiation? Okay, so you can read many places the proof for product rule of differentiation. What is the product rule of differentiation? That is differentiation of fx into gx. If there is a function fx, there is a function gx. If I multiply these two, fx into gx whole, what is the differentiation? Okay, one is area philosophy, but the proof, that's why I say that all our proof are different, all our videos are different. This proof probably you will not get. What is the conventional proof that is provided in books or other places that you can see? Okay, so fx into gx, fx into gx. If I do multiplication of two items, then it is as good as you are calculating area of a rectangle where these two items are side of the rectangle, or if these two items are orthogonal to each other, then multiplying would give the area. Okay, consider this as the kind of surface. This is gx. Okay, this is gx, and this is fx. This is gx and this is fx. Okay, if I say fx into gx, then this gives me full area. Simple, right? If this is gx and this is fx, if I say fx into gx, then it gives me full area. Considering if fx in or in other terms, if fx into gx is area of a rectangle, if fx into gx is area of a rectangle, then fx and gx are side of the rectangle. Or if I have multiplication of two items, 5 into 3. What is 5 into 3? Then take a rectangle whose one side is 3 unit and another side is 5 unit and calculate the area. Then area is nothing but 5 into 3, whatever is suitable. Take a rectangle whose one side is fx and one side is gx, then whatever the area is, that is fx into gx. So we are trying to find out area of a rectangle whose side are fx and gx. Okay, now we are trying to calculate differentiation. D and in bracket fx into gx by dx. D in bracket fx into gx. D in bracket fx into gx divided by dx. Okay, d fx into gx divided by dx, differentiation of fx into gx by dx. Okay, if that is the case, dfx into gx by dx, then consider this differentiation. This differentiation brings some some amount. If I have a function fx equal to x square and gx equal to x, then differentiation of x to the power x square into x is nothing but differentiation of x to the power 3. That brings 3x square. So it brings some amount, that is 3x square. fx into gx brings some amount. Whatever it brings the amount, consider that amount brings delta x chain along gx. So if this is gx, then there is a delta x chain along gx. Then there is delta chain along gx. Now full length is gx plus delta x. Gx plus delta x. If that is the case, then it brings delta y chain along fx. So if this is fx, if this side is fx, then there is a delta y chain along fx. So this full height is fx plus delta y. This width is gx plus delta x. Please understand again. If I have a function that is multiple of fx and gx, fx into gx, fx into gx. If I do differentiation of fx into gx, it brings another algebraic equation. Whatever it brings, in that, the share for the gx is delta x and share for the fx is delta y. If that is the case, then along gx we have delta x width more, and along fx we have delta y height more. But that is all right. But at the corner, this is how it will. If it grows like this, then it will go like this, and then it grows like this, then it goes like this. So at the corner, if you see the small area, that is delta x into delta y. Otherwise, this full width is now gx plus delta x, and this full width is fx plus delta y. Okay, so that is the concept. So fx plus delta x, fx. So this area, this this area is, this length is, gx plus delta x. This length is fx plus delta y. How much change in area that happened? If I see, if I take this side, then how much is the change? That is height into width. That is height into width. So height is fx into width is delta x. Delta x is nothing but dgx by dx, because it is the part along the gx. When I had differentiated fx into gx, and differentiation brought some amount, the part of the gx is delta x and part of the fx is delta y. So delta x is nothing but dgx by dx, that is the part of the gx, and delta y is part of the fx, that is dfx by dx. So what area we got more now? If this is the width, then what area we got more? That is the width, that is this height into dgx by dx. If this is gx, then the delta is dgx by dx. So height into width, fx into dgx by dx. What about this area? Then it is this width into delta y. Then that is gx into dfx by x. And what about the corner increment? That is dfx by dx into dgx by dx. Very small amount. So now the differentiation of by part, I'm not talking about first principle. Through first principle also we can prove it. As we don't like first principle, delta x tends to 0 or whatever. So dfx differentiation of fx into gx by dx is now fx into dgx by x plus gx dfx by dx. I repeat, the differentiation of gx into fx is dfx by dx into gx plus fx dgx by gx, or fx dgx by dx plus gx dfx by dx plus dgx by dx into dfx by dx. That is the corner one that we are saying. Otherwise, this is fx dgx by dx, and this is gx dfx by dx, and this corner one is delta x into delta y. When delta x tends to 0 and delta y tends to 0, then this would resolve in 0. So the product rule is proved as the differentiation of fx into gx equal to dfx by dx into gx plus fx into dgx by dx. So this is what the product rule is. Are you satisfied? This is what is available in all the books. This is what is available in all the books. Are you satisfied that delta x into delta y, when delta x tends to 0 and delta y tends to 0, then that part, this part is 0. Okay. Next is we can try with the first principle. So first principle say that if I have a function fx, then its differentiation is fx plus delta x minus fx divided by delta x. That is the differentiation, that is the first principle. So if I take fx into gx, then fx plus delta x into g x plus delta x minus fx fx gx divided by fx gx divided by delta x. Okay, so that is the kind of solution that kind of it is provided through first principle. So we will talk about first principle because this is not my priority. Fx plus delta x, fx plus delta x into g x plus delta x minus fx gx divided by delta x. Okay, so that is kind of more or less, we will talk about it. If it changes, we'll talk about it. This is more or less the first principle. Anyway, what is our proof? That comes into question. What is our proof? What is the lacking? If I kind of go with the first principle also, then we will land up in showing, then we will again land up in showing that delta x into delta y is 0 because delta x tends to 0 and delta y tends to 0. Same thing what did here. I don't know why there is another. Okay, we will go by the same proof that if this is gx and this is fx. Okay, if this is fx and this is gx, then kind of we will go by area only, but understanding is different. What we are trying to prove? We are trying to prove differentiation by part through area. Fx into gx, consider it as a, that is area. So we are trying to find dA by dx. This is what we are trying to find. dA by dx. dA by dx. Okay, dA by dx. If we are trying to find dA by dx, then what would be dA by dx? What is dA by dx? If this is area, if this is gx and this is fx, if this is gx and this is fx, then this is a. This is a. dA by dx. dA by dx. If I change one unit in x variable, there is x variable somewhere. This is not x. This is gx. This is fx. This is a. Someone can call it ax. Okay, a and in braces x bracket close. Ax. So if this is fx, if this is, sorry, this is gx and this is fx, then this is a. dA by dx. If there is a unit change in x variable, if there is a variable called x and there is a unit change in x variable, if there is a unit change in x variable, then how many of unit change that is seen in a? dA by dx. dA by dx. If one unit change is seen in x, then how many unit of change will be seen in area A? Consider that is delta A. If there is 1 unit change in X is seen, then how many unit change will be seen in A? Consider that is delta A. Then this area, if there is 1 unit of change in X is seen, then this full area will change delta A unit. Delta A is meter square if X is meter. If that is the case, now consider delta A is summation of two things, that is delta A1 and delta A2. Delta A is summation of delta A1 and delta A2, or delta Fx, delta A of Fx plus delta A of Fy, delta A of Fx and delta A of Fy. If that is the case, then what is delta A1 and what is delta A2? One is Fx part and another is Gx part. Delta A Fx plus delta A Gx, or delta A1 plus delta A2. I'll repeat it. D of Gx into Fx by dx. Gx into Fx is nothing but this area. That is dA by dx. dA by dx, if there is 1 unit change seen in independent variable x, then how many unit of change is seen in area A? A is meter square where x is in meter. If this is area, if this is area, then delta area change is seen. If this is area, then delta area change is seen in the dA by dx. If that is the case, then consider delta area. Delta A is summation of two area, delta A1 and delta A2. That is delta A1 plus delta A2. If that is the case, then delta A1 plus delta A2. Delta A1 we consider as delta A Fx, the area that belongs to Fx, plus delta A Gx. So A1, delta A1 is delta A Fx and A2 is delta A F Gx. What is the area that changed for the Fx? Along the Fx. The area, if this is Fx, if this is Fx, if this is the Fx, then area that change for the Fx is this portion. Can we see it? Along the Fx, that area change is this one. Delta A2 along the Gx, that area change is this one. Okay. What is the difference? There is a difference. Earlier, we talked everything about independent, we talked everything about x, gx and fx separately. Now we are talking everything with area perspective, not separate. That is the difference. Okay. When we go in multivariable case, multifunctional case, try to consider one component, not two components, always. So if I consider fx, gx separately, then change in gx is delta x. This is what we saw, and f change in gx is delta x, and change in fx is delta y. But we in this approach we saw that there is a corner that comes into the picture. This corner, so that is that area is delta x into delta y. This corner will not form. This is what I am saying. Corner will not form if explanation happens through area. Rather than dgx fx by dx, consider d area by dx. Then it will bring delta a. If there is a delta a, then it is delta a1 plus delta a2. Then delta a1 is nothing but delta a fx plus delta a gx. if this is fx, if this is fx, then along the fx, this is the area, this is the area that got changed. This is delta a1 along the gx, gx. For the gx, what is the increment in the area? For the gx, increment in the area is this, that is along the gx, that is a2. So this is a1, delta a1, and this is delta a2. If that is the case, then this corner one will not come. If we approach through area way, then this corner, what we were seeing, then this corner, then this corner will not come. If this corner will not come, then we are not tackling only right delta a1 and delta a2. What is delta a1? Delta a1 is fx into dgx by dx, and delta a2 is is gx dfx by dx. So I believe it is crystal clear that differentiation of fx into gx is nothing but fx and dgx by gx plus gx dfx by dx. Differentiation of gx into fx equal to fx dgx by dx plus gx dfx by dx. Okay, so we proved it through area fundamental, where we are not getting the corner one. So that is delta x into delta y. So this corner one, what we were getting earlier with philosophy, that this is delta x change and this is delta y change. Change, if this has area change, then this area change happens in one side and in another side. Along one side with, there are two sides, right? So area change will happen in one side and in another side, and that is delta a1 and delta a2. So that is the differentiation product rule in differentiation. Okay, we will fulfill kind of first principle also, that is if we want differentiation of fx, then fx plus delta x minus fx divided by delta x, or fx plus delta x minus fx minus delta x divided by 2 delta x. So that principle, that is first principle, there also we will see there is a caveat, there is a gotcha. So that is the concept. So we proved it through area way also. The differentiation of fx into gx is f dgx by dx plus gx dfx by dx through area way. This is not the limit. We have many more proof for the differentiation product rule in the differentiation. Then we will kind of, if we have the product rule, then we will go with the, there are three. There is one multivariate version is there. There is one differentiate, then there is one polynomial version is there. There is one logarithmic version is there. There are so many. We will see one by one. And then first principle, what we have said through first principle also, we will prove it, and then we'll see delta x and delta y tends to 0. So we will not only that, then integration by part or chain rule or product rule in integration, we will prove through this only that how product rule in integration arrives. So that we will see.